Greetings. So, in our previous class we talked about quantum entanglement, and we came to terms with the principle of superposition in quantum mechanics, the entanglement that it leads to, and the fact that it seems to be real in the sense that the uncertainties you are led to in quantum theory cannot be accounted for by any local hidden variables. So, this was the suspicion of the Einstein-Podolsky-Rosen argument, and this could be tested using the Bell inequalities. So, now we know that quantum theory predictions of actual measurements in laboratories are consistent with the predictions of quantum theory, and they violate the Bell's inequalities, and therefore, the simultaneous applicability of counterfactual theory and local hidden variables would not be compatible with what you see in the lab. And this has impacted both science and technology in a very big way, and particularly of importance at this time because quantum computers are around the corner. And as we all know, it all started perhaps with Charles Babbage and then Alan Turing and so on, and more recently Feynman. So, before we get into it, the first lecture will be like a warm up lecture to reflect back on what are classical computers and how computing is done using traditional computation. And I know there are experts from computer science over here, so you would know it all, but then there are some others who also I am sure will be familiar with this. But this will be like revisiting a topic which is well known, but it will set the platform for subsequent discussions. So, that will be the first lecture on this topic now. And we go back to George Boole in the middle of the 19th century. He came up basically if Newton connected mathematics and astronomy, George Boole connected logic with mathematics and arithmetic in particular. So, the reasoning, the deductive reasoning and mathematical logic was transformed into symbolic logic and subsequently into a mathematical composition of logical ideas. So, it was basically a thesis on laws of thought and the mathematical theories of logic and probabilities that he published in the middle of the 19th century in 1854. And the symbolic mathematical expressions that he developed eventually became the basis for modern computers. And what impacted technology in a very big way was this work of Claude Shannon, because he recognized that the symbolic logic and the Boolean algebra could actually be put into hardware, because electrical switches are either on and off, and using this you can actually develop electronic circuits which are driven by this symbolic logic, and it became possible to compose the powerful machines using this digital circuits, and eventually of course based on the switching circuits using transistors and so on, one could build modern computers. So, these are the classical computers, and they work on the idea that a switch is either on or off. So, it is just a two-state system. You can call it as up and down or head or tail. It is a binary thing, which is why the unit is a bit. Okay. and it is either true or false. In most signals it is either long or short, and whichever way it is just one of the two. And using this, Boolean algebra can be exploited to do any analysis of any kind of logical thought process, which is really amazing. Means it could be anything. It could be the Euler's algorithm to find the greatest common divisor, for example. And you can set up a flow chart, and no matter what problem you are dealing with, you can sort of break it down into yes no options and then take alternate paths, and using these alternatives arrive at a logically correct conclusion. So, this is really amazing that what just a two-state system can help you do, either yes or no. You decide, either you go left or right, and if you take that decision in a logically consistent fashion, you will be led to the correct answer. And this can be done with any complicated problem, no matter how complicated it is, which is really amazing. That's any thought process that goes on in your brain, no matter how complicated it is. Okay, you are confronted with extremely complex issues. It could be a physical problem or any other kind of problem. All you have to do is to analyze it in terms of yes or no, 1 or 0. It can be a very perplexing conundrum like Arjun had. May I fight the war or should I not fight the war? Whatever. Okay? Or it could be Hamlet's question, to be or not to be. Okay? Any of these questions boil down to an analysis based on 1 or 0, which is why the Boolean algebra, Shannon's work and so on become so important, that anything can be done using 1 and 0. Shakespeare did not know about our quantized cat. Is the cat dead or alive? All right? So, at that time there was no quantum theory. And this classical computers are then based on this 1 or 0, and you can do everything in terms of 1 or 0. Normally we use the base of 10 because of the 10 fingers, but you could also do it on the base of 2. We have 2 hands, and these are the reasons the base 10 and base 2 are so commonly used, although one can use other base systems also. And a number like 7349 can be written in terms of combinations of various powers of 10. So, you just sum up 10 to the power 0 with 10 to the power 1, 10 to the power 2 as many times as you need, and then come up with this number. So, this is the usual one that we use in our everyday life, but you can express it also in terms of some other base, and the base which is commonly used is the base of 10, base of 2, and you can sum up 2 to the power 0 once with 2 to the power 2 4 times and 2 to the power 4 16 times and so on, right. So, you can take as many of these powers as are needed. And how many times do you need them? You need them, those many times as are indicated in the bottom row. Okay? And you need them either once or you do not need them at all. And depending on how many times you need which power, you can write the same number in the base, at the base 2. So, you can write anything in powers of numbers to the base 2 or 10. And you can do it not only with numbers, you can have an ASCII kind of code, and then you can have letters, symbols, and so on written in zeros and ones. And you can put every information, whatever, in these terms, including colors and whatever. You can also write numbers which are smaller than 0, okay? And you can put them in powers of 2, but inverse powers this time, and you can still use this system just the way you use the decimal system. So here essentially you have 0 and 1 two options, and they correspond to an electrical switch being on or off, and you can have these switches in parallel or series, and then develop an electronic equivalence of the Boolean algebra, and then develop digital circuits. So there are 3 fundamental Boolean operations. These are the not, or, and the third is and. And using these, you can then develop combinations also. So there are various symbols which are used. These are the common symbols which are used for these operations, which you would have used in your introductory electronics or computer science courses. Okay, so some alternate symbols are also used, and basically they represent elementary fundamental logical operations of either negation or combinations like union, or intersections or multiplication. Okay, so these are the fundamental Boolean operations. And then using the 0 and 1 and symbolic logic, you can generate these truth tables. So if you have 2 inputs x and y, then depending on what combinations you have of the 2, you will have a net result which will be either true or false. So 1 represents true, 0 represents false, and you can develop these truth tables. So using these operations, you can develop some additional logical gates, as they are called, because a gate is what allows certain thing to go through and stops something. So it's a logical gate, and you have these electronic gates or the Boolean gates, and depending on what kind of combinations you make, you have different kinds of logical gates, and these are represented by symbols which most of you would be familiar with. So you have a buffer which doesn't do anything really. Then you may have a negator, a NOT gate, which is represented by the buffer with a circle put at the head of it, all right. So if the input is 0, the output would be 1, and vice versa. So this is just doing the opposite, which is what you like to do when your parents tell you anything. So that is the NOT gate, right? Then you have the AND gate, the 2 input AND gate. So it requires 2 inputs, and the output of the AND gate would give you the truth value 1 only if both the inputs are 1, not otherwise. Okay, so that is the necessary condition to get the truth value 1, otherwise it is always 0. Then you have the OR gate, in which the truth value is unity if either or both of the inputs are on. Okay, any one is enough, but if both are on, then also you get output 1, not otherwise. Then you have the NOT AND, Okay? And this is just the opposite of the AND gate. So, you take the AND gate and just negate it. So, that is what you get. Then you have got the NOR gate, which is the opposite of OR. So, notice that when either or both the inputs are on, the output is off, and the only time it is on or with a truth value 1 is when both the inputs are off. So, this is the NOR gate. Then you have the exclusive OR XOR. And what the exclusive OR does is that it gives you a truth value 1 when either of the two inputs is on, but not when both the inputs are on. And of course, when both the inputs are off, it would give you 0. So, this is the exclusive OR. And then you have the exclusive NOR. So, you can see that this will give you unity either when both the inputs are on or both the inputs are off. If either of them is on and the other is off, then it will not give you on in the final result. Okay? So, this is the exclusive NOR, and then you can carry out further combinations of these gates, and that is what helps you design very complicated electronic circuits and all the modern electronics in which you have all these gadgets. So, these are built from transistors which are employed to implement this symbolic logic depending on what end result you require. And using these, you can construct extremely complicated electronic circuits, and all the modern gadgets which you are carrying in your pockets make use of this with a large number of transistors, hundreds, thousands, tens of thousands on tiny chips, and that has impacted life at every level. So, the symbols can be different sometimes in literature. There are traditional symbols, and then there are symbols which are approved by the IEEE, right, the Institute of Electrical and Electronics Engineers. So, they have approved some symbols. So, sometimes in the literature you will find different symbols used, but they all mean the same thing. So, the AND gate is represented one way or the other, but as long as you know what symbol represents what, you can figure out what logic is involved. So, you have these traditional and IEEE symbols of different kinds, okay? And then using these, you can develop more complex gates and more complex electronic circuits. So, very complicated electronic circuits can be built, okay, using just 1 and 0. This is amazing. This is really amazing. Means what goes at the foundation is nothing except just yes or no, 1 or 0. Is the switch on or is it off? Nothing else. You can have 3 input gates, okay, and then develop the Boolean algebra corresponding to it, and then develop corresponding electronic circuits. And then, thanks to the Carnot maps, who was a physicist, a mathematician, and a computer scientist, so you can combine a large number of operations and put it into hardware circuits, okay? And using these Carnot maps, using special techniques, the minimal sum of products and so on, then you can develop very complicated electronic circuits, and that pretty much brings up the summary of what the classical computers are based on. And this, of course, led to some of the brilliant works by Alan Turing, and I will comment on it in the next class after I let these foundations of the classical computers in terms of the 1 and 0 to sink in. And Turing made some path-breaking work in the last century. It's too tragic that he had a very short life, but during that short life, what he contributed was incredible. And he even made a prophetic statement that this is only a foretaste of what is to come and only the shadow of what is going to be. So some of you might have read this quote attributed to Turing. It's a very famous one. So we will take it up from here in the next class.